Hello all, welcome back to part B of lecture 15. In this uh, discussion, we are going to see a demo of how to implement Gaussian process regression from scratch using R. So I'm going to start my R. I'm going to open an R script. So first thing I'm going to say that remove just this list anything if it is there ls. So anything if there is any later, if I have any, just clean the environment. Essentially I'm going to say install or load mvt norm package. Let me see, I hope it is there. Yeah, it is there. Then I'm going to set up a seed. So let me just draw a random sample between a number between 1 and say 10,000. One sample is good enough, 2604. So I'll just pick this random number and set as this. I'm setting this number so that when you will use this number, you will get the exact same answer. Then I will decide a simulation size. Of say around 500, I think. Okay, that many data points we will simulate. Okay, so first I'm going to define x variables, sequence of number between say minus 15 to 15 and length length dot out equal to capital N. So if you just run this, so now you can see, if you just run x, you can see there are 500 samples, 500 values are being created between minus 15 and 15, each are of equal width, equal interval. Okay, now I'm going to draw a random samples, bunch of random samples, say E equals to R norm, how many, n many, with mean equal to 0 and is d equal to 0.15. okay, and then I'm going to write f of x. F is sine of x by x, and then if I just run this, and then now y is equal to, y values are my whatever f plus e, f of x plus e, correct? Now if I plot x comma y, cex equal to 0.3. so I can, let me zoom this. Okay, let me just zoom it. So you can see all the points are around this. Okay, and in fact you can make it pch equal to 20, maybe color equal to red. So this will be a little brighter, or we can just increase the value a little bit. Cx, yeah, it's slightly better. Okay, looks much better. Okay, so now this is my plot, this is my data. Now we are going to pretend that all we have is x and y. We are going to pretend all we have is x and y. Okay, all we have is x and y, and we do not know the true relationship between x and y. So given the data, can we pick up this completely? There is no trend actually, there is bunch of seasonality, and most of the values are hovering around 0, and then there is at 0 there is a signal, boom, there is a burst of a signal, and then it came down, and then again it is sort of a hovering around 0. So can we capture this complete non-linear behavior using GP regression? Okay, so this is our idea. So now what I'm going to do, we are going to create a data set. First thing what we will do, we will just say cbind data.frame x comma y. So here is my data, x and y's, and these are the, so now we have a data which has one x and one y, and we are trying to fit a model out of it. So the first thing is we will fit a Gaussian process regression, and we will model it from scratch. There are some built-in packages are there, but I want to understand. If you use built-in package, you will not really understand how GP regression really works. Okay, so what I'm going to do, I'm going to teach you how the GP regression works. So best way to learn is do programming from scratch. All right, so first thing I will do, write GP regression, negative log likelihood of GP regression, right? Negative log likelihood function of GP regression. Okay, so G log like equal to function y comma x. Okay, and then no, the way we will do is theta and d. So d for data, theta is all the parameters. So what we will do is y equal to d comma y and x equal to d comma x. Okay, and let me just write, let me see if it is actually working. Okay, so the best way of doing it is just write sum y print, okay, print sum of y and print sum of x. Okay, so let me just run only this part and negative log likelihood and say 0, 0, 1, that will be for theta, and d equal to data. yeah, 57.73 and some very close to 0. So if I take data, just check data $x, if I just take sum of that, and they're exactly matching, and then if I just take sum of data $y, 57.73925, so they are exactly matching. So that means this part is happening absolutely correctly. So I can delete this part and I can delete the print also. Okay, so now we have tested it. That means this function reading the data correctly. Okay, so next thing we will do n equal to n row d. Okay, and I think that will be not a problem. And so read the data. This is first, these are the three things I think. First is read the data, and in this GP regression we are going to use exponential covariance function. So let me write it down explicitly. We will use exponential covariance function, also sometimes known as RBF, radial basis function. Okay, so now, and that will have three parameters in that covariance function. So read the parameters of the covariance functions. Read the parameters of covariance function. Okay, and what are those? First is sigma. Okay, sigma equal to e to the power theta 1. And why I am taking e to the power theta 1? What happens eventually, I want to put it through a optimization subroutine. I'm going to call the optim function in this case, and in the optim function the theta will be expected to be varying from minus infinity to infinity, but I want my sigma obviously on the 0 to infinity range. So as soon as I get the theta, I will transform it and then I will use it. So we will get we will effectively optimize a transform variable or transform parameter. Then next is rho. Rho is e to the power theta 2 and tau. Tau is equal to also exponent of theta 2. Okay. Now what I'm going to do is I'm going to calculate the distance matrix. Let us first calculate the distance matrix. So DIST, where effectively what I'm going to do, call the dist function available in the R. So dist x method equals to Euclidean diagonal equals to true, and also I want the upper part of the distance matrix as well, and I want to store it as a matrix so that I can do matrix operation on it later when we will do the optimization. Okay, so this is the distance matrix, and then I'm going to compute the covariance matrix sigma. Let's compute covariance matrix sigma. Okay, what is covariance matrix sigma? So sigma is essentially the sigma parameter we have just read here, sigma parameter times e to the power minus rho times absolute value of the distance. So in fact, what I can do, I can take the absolute value here so that you will, or I can just write it. I don't want to make it too big. Distance I can equal to ABS distance, or it doesn't matter actually, we can just have it here. I think this is fine. And diagonal of tau where n rho equal to n. Okay, now mu, I'm going to say that replicate mean of y as a function of n. Okay, and then I'm going to write negative log likelihood, evaluate negative log likelihood as function of negative value of first dmv norm y as a mean equal to mu, sigma equal to just capital sigma, and log equal to true, and I have to have a negative sign in the beginning and return negative log likelihood. Okay, so this is the function. Let me just call this function. Okay, and try to evaluate this function at some initial value. So this gives me one value, this could be another value. Okay, 1138. So at some initial values it runs and it gives you some good things. Okay, now next what I'm going to do, I'm going to write optimization. Now I'm going to write some optimization technique. Optimizer. Actually, we have to put some prior on the top of that, otherwise the optimization might throw some error. So let's define, so this is my negative log likelihood. So let's write some, this was negative log likelihood function, and then negative log prior we have to write. So we will do negative log prior function we will define as function of theta only. Okay, it will not be function of data, it will be only function of theta. And what I'm going to do is just copy these few lines at the beginning from the knock likelihood and paste it here, and then P will be, say, d gamma. Let us suppose these are all d gamma sigma equal to comma 1 log equal to true, then minus all I have to just do row and then, so actually what I can do instead of saying that, I can just take, since I'm giving the same prior, let me just write it down in any way, because later if you want to change anything you can change by yourself. Because suppose you decide that okay, on row I don't want to put a gamma, I want to put, say, uniform between 0 and 5 or something like that, that you can do. So if I want, you can give a, say, uniform between, say, 0 and 15. Okay, so you can do that, or 0 and 10 maybe. So you can do this kind of thing and then eventually return. So you can assign a choice prior of your choice, so return P. So this is my negative log prior. Okay, and then finally negative log posterior, which will be simply negative log posterior function theta comma t and NLP equal to, first what I have to do is basically negative log likelihood comma theta comma d plus negative log prior comma theta and return NLP. Not natural language processing, it's negative log posterior. Okay, and if we run this negative log posterior, let us check if it's working perfectly fine for at least these values, the initial values. Okay, it's working reasonably okay. We can try one, and I think this is working perfectly fine. All right, next what I'm thinking is that essentially what we need to do, we need to find, so what we will get, that posterior mode, obtain the more posterior mode, or obtain estimates, parameter estimates using optim. These are typically posterior mode, obtain estimate using optim or posterior mode. These are all posterior mode as estimate. Okay, posterior mode as estimate. It's not MLE. If you have to MLE, you have to optimize negative log likelihood function, but we are going to optimize the negative log posterior function, so we will get posterior mode. We will try to obtain both, and we will try to see what are the differences. So first, sometimes posterior mode also called map estimate, maximum a priori posteriori estimate. So map equal to optim. Okay, and so we have to have some initial value of theta. Let us take this initial value, theta dot initial. Okay, initial value of theta. So let me provide first the initial value of theta, and then negative log posterior, and then what we have to give, t equal to data. Okay, so it takes few minutes, maybe a few seconds. All right, and then from there, theta hat, we have to, so if I just run the map, so you can see that it gives me 3 estimates. This is the value, at optimal value, the negative log posterior in these estimates, and convergence equal to 0 means there is the convergence did happen, and it has not find any problem with the convergence. The optimization didn't had any problem. So theta hat equal to, from the map, now what I will do, I will just extract the parameter, optimized parameters. Okay, and then my theta hat are, these are the values, and then what I'm going to do, sigma hat equal to e to the power theta hat theta hat 1, that is my sigma hat, and then rho hat equal to e to the power theta hat 2, what is rho hat, let me see, so 0.21, and then tau hat equal to e to the power theta hat 3, so tau hat. Okay, so we got the estimates. Now we have to have the distance. Remember that we calculated this distance matrix out of the box. Okay, out in the function, we have not done it in the out in the environment. So we have to just calculate that. So now we have the distance n equal to n row of the distance, and now first we have to calculate sigma. Okay, capital S sigma hat equal to, first sigma hat times exp. So remember that we want this function to be here. So sigma will be replaced by the estimated sigma hat, rho will be rho hat, and tau will be by tau hat. Now that gave us sigma hat. Okay, so remember sigma is a very large matrix, going to be, this is a very large matrix of, if you just say dimension of sigma hat is 500 by 500, remember that. And then y hat then will be sigma hat times exp minus rho hat times distribution. Okay, percentage star percentage solve sigma hat percentage star percentage y. So if I just run this will be my y hat. And now what I'm going to do on the plot, let me just bring that plot that we have done here. Let me just bring that plot here. Now I'm going to write lines x comma y hat. Now I'm going to make x comma y hat color equal to blue maybe, and L width equal to maybe 4. Okay, so if you just run it, yeah, so you can see, let me just, so you can see that it's a bit jittery, but it is actually picking up to an extent. Let me plot the original curve here. Let me plot the original curve here. Okay, say lines equals to x comma y f. F is the original curve, I think, and we can take some other color equal to maybe some other color, maybe black. Okay, and line width equal to 2. So if you now, let me just, you can see this black color is the true curve, and this blue curve is the estimated f hat, and that f hat is essentially very close. Now what I'm going to do, we will see that as the sample simulation size increases, so instead of 5000, if I just increase the simulation size to 1000, that will make the curve much more, we'll see how the curve will behave. If we have 5000 samples, so it will take a little bit time because we have more samples now. So it might take about a minute. So if you, let me just increase it. So this is with the 1000 samples, you can see, and if this is with the 10,000 samples, 500 samples, this is with the 500 samples, and this curve is with the 1000 sample. So almost the 1000 sample, probably a little bit closer. So the GP regression has no clue what is the true original relationship between X and Y, and yet the GP regression actually picking up the actual relationship between X and Y. So this is a very strong and very useful methodology if you want to do nonlinear regression. Now you can ask me, if you have only one X and then we know how to do that, can I do it for more than one X if I have multiple X? The answer is yes, you can do exactly the same way. Only thing is you have to calculate the distance, but we know how to calculate the distance. And here we have used Euclidean distance because it was a simple toy problem. Sometimes you may have to be a bit careful about what kind of distance function you want to compute. For example, if you are using a spatial data, you may have to use earth distance. But if you are using, say, a categorical data, then you may have to use appropriate distance like Gawar distance, which do calculate the distance between the categorical variables. So you have to be a bit careful about what kind of distance functions that you want to use. But if you are sure this is the correct distance function that you want to use, then perhaps Gaussian process method or Gaussian process regression is one of the best methodology that you can think of. So with that, I will stop here in this video lecture. Let's see you in the next video.